So problem 4.3, this one is related closely to problem 4.2, and if you have not done problem 4.2 yet, I strongly recommend that you try that one first before trying this problem. So let's see what this problem says. We are given a function w of two variables x and u, which is of this form here. Now, just to understand this function better, x and u could be vectors. So let x be in Rn and u be in Rm. So w then maps Rn cross Rm to R. Okay, so to R meaning a real number or a scalar. So this is a scalar valued function. And what is additionally given is that n is symmetric, positive, definite. What I will assume additionally is that m is also symmetric. It could be an additional exercise, but even if m is not, you can replace m by m plus m transpose over 2 and still have the same value of w. You can check this. Now the problem is to solve this minimization problem. So we want to minimize over all possible u, w of x comma u. X is assumed to be fixed or given. Now if we write this w of x comma u explicitly, we get the following: mx plus lu and L transpose x plus nu, which is nothing but x transpose mx plus x transpose lu plus u transpose L transpose x plus u transpose nu. Now note that this is a real number or a scalar, and observe these two elements or entries. You have x transpose lu transposed is equal to u transposed L transposed x, which is this element, this term. And because they are scalar, the transpose of a scalar is the same scalar. So we have this function equal to 2 times x transpose lu plus u transposed nu, w of x comma u. Now this is an unconstrained minimization problem, so a necessary condition for optimality if w is differentiable is to just set the gradient to 0. And this is just like you did in calculus. If you want to minimize a smooth function f, you can just set the derivative to 0. But now we are dealing with vector valued variables, so we will use some results which I just write down here. If m is symmetric, then we have d by du. Sorry, if n is symmetric, then we have d by du of u transpose nu equal to 2nu. That's the first result. And the second result is d by du of some constant vector c transposed times u is c. So we will use this now to set the gradient of w to 0. So the gradient of w with respect to u. Now if you observe this term, it's independent of u. So the first term set to 0. The second term, using the second rule, we have 2 times x transpose L transposed. And the third term is just this. We obtain 2nu. And now we want this to be equal to 0 at optimality. So we can cancel the 2 first, then we have nu at optimality. Let's call this u star. So at optimality nu star must be equal to minus L transposed x. And because n is positive definite, we can invert it, because all eigenvalues are non-zero, or rather positive for a positive definite matrix n. We can obtain this as the optimal u star. So once you have this u star, we can calculate the minimum value of w by plugging this in to obtain x transpose u star transposed ml transpose n. So x and u star to obtain have this. I've pulled out x outside, and now we can just evaluate this. N inverse will get cancelled here, and so will this term. To obtain x transpose m minus L n inverse L transposed x. So we have solved problem 4.3 with the first method. Now we move to the second method. So now let's solve problem 4.3 with an alternative method which builds on problem 4.2. So let's first recap what we saw in problem 4.2. We saw that a t of this form led to T transposed ML L transposed N T to be equal to a block diagonal matrix with blocks M minus L N inverse L transposed and N on the diagonal. Now let's call this matrix X, this matrix Y. We will additionally use this fact that if T is of this form, I0 P I, then T inverse is I0 minus Pi, and you can verify this by checking T inverse is equal to T inverse T is equal to identity. Now what we have is T transpose xt equal to Y, where Y is block diagonal. So we can write X as T transposed inverse Y T inverse, where we pre-multiply both sides by T transposed inverse and post-multiply by T inverse. Note that this is possible because T is invertible. T is invertible because T is lower block triangular, and along the blocks we have identities, so all eigenvalues are 1. So no eigenvalue is at 0. So this is nothing but T inverse transposed. You can also try to show that T inverse transposed is equal to T transposed inverse. And now using this rule that we just saw, T inverse is basically just I0, cancelling the negative sign now, I transposed times Y times I0 and inverse transposed I, which is nothing but I L n inverse I 0 times Y times I0 n inverse L transpose I. So that is X. Now let's come back to our problem. We have W of X comma U given as X transpose U transposed M L L transpose N times XU. So this matrix is what we call X. So we can substitute for X this expression to get that our function W is given by I L n inverse 0 I times Y times I 0 n inverse L transposed I X and U. I have basically just replaced X by this expression that we just derived a while ago. Now this is nothing but, if I just carry out these two multiplications, I get X transposed and X transposed L n inverse plus U transposed times y x and n inverse L transpose x plus u. Now note that y here is block diagonal. I will just write the y explicitly now. Minus L n inverse L transpose 0, 0 and n. So this is nothing but x transposed m minus L n inverse L transposed x plus x transposed L n inverse plus u transposed multiplied by n multiplied by n inverse L transpose x plus u. So this is w of x comma u. So now once we have w in this form, let's observe that this term is independent of u. Let's call this w1 of x because it does not depend on u. And this term, because n here is strictly or rather positive definite, this term has to be greater than or equal to 0. And 0 only if this term is 0. So let's call this other term w2 of x comma u, and well, we know that this w2 is non-negative. So clearly w of x comma u is lower bounded by w1 of x because w2 is non-negative. This is the least we can have. Now if we choose u to be equal to minus n inverse L transpose x, we get w2 of x comma u to be equal to 0, which means w of x comma u is equal to w1 of x comma u. And we know that we cannot go lower than w1 because of this condition. So the optimal u has to be minus n inverse L transpose x. And also the optimal value of w at this u has to be w1 of x, which is transpose m minus L n inverse L transposed x. And this is what we were supposed to show in this problem. So we are done. So thanks a lot, and that's it for this problem. Yeah, in this short section, I'd like to talk about differentiation with respect to vectors. We are familiar with differentiation with respect to scalar valued variables. Let's have a quick look at these things when the variables are vector valued. So let's take u, a vector valued variable in Rn, and let's think of a function f which is mapping this Rn to a scalar r. An example of a function could be the norm of u. Note that this is however not differentiable. Another example would be C transpose U, where C is a constant vector also in Rn, or we could have a quadratic function which could be represented as U transpose Qu, where Q is a constant matrix of size n by n. Now we want to differentiate these functions, of course not the norm because that's not differentiable, but the other two functions with respect to the vector valued variable u. So first let's see what we mean by df by du, and we define this as a vector of partial derivative of f with respect to u1, partial derivative of f with respect to u2, and so on up to partial df by dun. So this is what we mean by df by du. It's also called the gradient of f. Now this df by du, often also represented by this nabla notation, is another function which is mapping Rn to Rn. Now let's look at the examples that we saw above. So example 1, if f of u is C transpose u, that is basically this row vector times a column vector. Now df by du is partial f partial u1 up to partial f partial un. Now you can clearly see that f can be written as c1u1 plus c2u2 up to cn un. So partial f with respect to u1 would just be c1. All other terms here would vanish. Similarly, partial f with respect to u2 would be c2, and so on up to cn. So what we have is df by du is the constant vector c for this example. Now a more formal way to prove this could be as follows. So f of u is sum over ci ui. Now partial f with respect to partial um is the sum is of course over I is ci ui. Now differentiation is a linear operation, so we can bring out the summation, and we have dui by dum. Because c is also constant, we can pull that out outside the differentiation, and now we can see that partial ui with respect to partial um is 1 only when I is equal to m and 0 otherwise. So we can write this as ci times delta im. That's how it's typically shown. Delta im is 1 when I is equal to m and 0 otherwise. So that gives us cm and all others 0. So if partial f partial um is cm, then partial f partial u1 is c1, partial f partial u2 is c2, and so on. to partial f partial un, which will be Cn, and this is what our gradient or df by du by definition is. So this was one formula that we used in one of the exercise problems. Now the second one was for this example. Now let fu be a quadratic function of u, that is u transpose qu, where q is a constant matrix of size n by n. Now note that this can be written as sum over I sum over j ui qij uj. So you can check this out later, that this u transpose qu could be written in this form. You can try it for a small example, for example if n is equal to 2. Now we do the same trick as before. Partial f with respect to partial um is, because again differentiation is a linear operation, we can pull it inside the summation to get partial uj with respect to partial um. Now we use the chain rule inside the summation to have partial ui with respect to partial um times qij uj plus ui times qij partial uj with respect to partial um. That now we can split the summations into two different summations. This is the same as partial ui with respect to partial um times qij uj plus summation I summation j ui qij partial uj with respect to partial um. Now again, as we did before, partial ui with respect to partial um would be 1 when I is equal to m and 0 otherwise. So we can just write this as delta im qij uj plus ui qij delta jm. Now of the summation over I, all the other terms except when I equal to m will cancel because of this delta im, because it takes value 1 only when I equal to m and 0 otherwise. So this sum reduces to sum over j q mj, because I has to be m uj plus, similarly here the summation over j will go away because of this delta. So then we have sum over I ui qim. Now that, so let's first note that qim can be written as q transpose mi. So I comma mth entry of q is equal to m comma ith entry of q transposed. So we have this term stays as it is, and in this term we have q transposed mi times ui. Now if we look closely, this is just uh, the mth row of q multiplied by uj, or in other words this is q times u, which is a vector, and the mth entry of that vector. Similarly, this one here is the mth entry of q transpose u. You can verify this later as well. So what we get finally is Q plus Q transpose times U and the mth entry. Remember that we were calculating T partial F by partial UM. So if we stack all of these on top of each other, we get df by du equal to, if we stack all the entries of this vector together, we get that vector back, which is u. Now for the problem, for the exercise problem, we additionally had that q was symmetric. So if q is equal to q transpose, then we additionally have df by du equal to 2qu. And that's what we used in the problem set. So yeah, that's it for now. Thanks.